Around 5 years ago, the most basic supply circuit created so much more voltage than I expected that it caused my design to fail. I did not see that one coming, having used these for over 25 years. To figure out what went wrong, I had to put this circuit on the bench and do some digging. So in this video, I'll show you exactly how transformers and tolerances can ruin your design and how to model them accurately so you can prevent these problems. So to understand what's going on, we first have to look at transformer models. Just ignore this, it's the running gag on the channel. Here you see a model of a transformer. It's an ideal transformer with a transformation ratio of 1 to X and 2 resistors. Rp for the primary winding and Rs for the secondary winding. These are just the resistances of the winding wires. I've never seen a datasheet reporting all of these numbers, so I'll show you how to measure and use them. Let's start with the transformation ratio X. I've hooked up a 225 VA transformer here with two 20 volt secondary windings that I connected in series to create 44 volts. The primary voltage Vin is controlled by an adjustable transformer which allows me to set the input voltage. It's not really necessary but makes life a bit easier. The primary and secondary voltages are measured using two multimeters as you can see in the picture. Since grid voltages move around a bit, I always take a picture to make sure both readings are taken at exactly the same time. So dividing the secondary and primary voltages gives you X, the transformation ratio. The output voltage is a bit higher than 44 volts because I realized this was a 220 volt transformer after I did the measurements. So the input voltage is 10 volts too high. This does not affect the transformation ratio though. The next thing we need are the winding resistances. You cannot just use a multimeter to measure it directly because the resistance can be very low and you'll also be measuring your measurement wires. The solution is to force a current through the winding, measure that very accurately and then measure the voltage across the winding, as you can see in the schematic. Again, I took a photo and when you fill in Ohm's law you get Rs. You can do the same for Rp, that turned out to be 5.9 ohms. Just to be complete, if you have a benchtop multimeter with a built-in 4-wire resistance measurement option, you can measure it directly. So you have all the parameters now. However, I'm going to add one more measurement because it'll allow us to determine the accuracy of this simple model by comparing measurements and simulations. And that is measuring the transformer under nominal load conditions. You can use the same setup to measure the transformer ratio, but now with a load attached to it. This load resistor has a value of 8.23 ohms. The primary voltage is set in such a way that the secondary current is 5.1 amps, which is the nominal output current for this transformer. Now you can calculate the transformation ratio again. It has gone down because of the load current causing voltage drop across the primary and secondary winding resistances. So we measure the transformer parameters in an unloaded condition. If this simple model is accurate, a simulation of the loaded measurement must give exactly the same results. Let's find out if it does. Here you see the results of the simulation. Let's start with the schematic on the left top. You see the transformer model which has the unloaded ratio that we found. This is 0.2164 and the primary and secondary winding resistances. There are two schematics, one without a load and one with a load. The pink numbers show the measurement results, the green numbers show the simulation results. Red shows the errors. You can see how ridiculously accurate this model is for predicting what's going to happen in real life. To be complete, I've added the simulation waveforms for both cases. Red is unloaded and green is loaded. And the derived RMS values for these waveforms. Next to predicting exactly what kind of voltages you're going to get under different load conditions, it's also great for simulating startup currents of linear supplies. This is especially useful if you have large value capacitors connected to the supply, like with audio power amplifiers for instance. This is why I teach my students to model transformers before building supplies. It prevents unexpected surprises. So you've seen that this model is very accurate, but since the datasheet does not give you everything, you have to do some measurements to get it. This is annoying as you'd have to buy the transformer first. So let's see what we can get from a transformer datasheet. So here's the datasheet for the toroidal transformer you've just seen. The first interesting parameter is regulation. This shows the percentage voltage difference between the unloaded and loaded condition, just like we measured. It states 7%. You can compare that with the measurements we did. When you divide the transformation ratios you measured in both conditions, you get 7.2%. So that is very accurate as the datasheet states 7. So winding resistances are not given, but if you assume that all the loss takes place in the primary winding, you can use this 7% to calculate a theoretical primary winding resistance and set the secondary winding resistance to 0. This is accurate for modeling as long as you have a single primary and secondary winding. If you have multiple secondary windings with different loads, the accuracy will be reduced. There are more advanced methods, but none of them are really accurate, so I won't discuss them further here. So what about transformation ratios and datasheets? Datasheets will show the primary and secondary voltage under nominal load conditions. If we divide 44 volts and 220 volts, we get 0.2 as a ratio. The measurements showed almost the same number. That is a 1% error, which is pretty good. So up till now you've been looking at a high power transformer. These behave quite nicely. The supplier you had problems with used a tiny PCB transformer. These behave a lot worse. Let's analyze two of them. Here you see two equal 2.5 watt PCB transformers. They have two primary and two secondary windings, so they can accommodate 115 and 230 volts. The first thing that stands out with the triode transformer is regulation, 25%. This means the voltage without a load is 25% higher. That is quite extreme. The second thing that stands out is that the Hammond datasheet shows nothing about regulation. I really tried to find it, so here you'd be completely in the dark. As you can see, the resistances of the two primary windings are not equal. The same is true for the secondary windings. This feels a bit weird, but is probably caused by the wires of these windings having different lengths. The number of windings must be the same, but the second layer of windings has a larger circumference, leading to more length and more resistance. This is just my guess here. The bigger problem here, however, is the regulation. 31.5% instead of 25%. This means the unloaded voltage is 6.5% higher than you would expect based on the datasheet. So how did this cause me problems? Let me show you how this works out in a linear supply circuit. In this supply you expect the output voltage to be the secondary RMS voltage times the square root of 2. This gives you 25.4 volts. You lose about 1.4 volts across the bridge rectifier, but let's ignore that for now. Now you take regulation into account. In this case it's 31.5%. This results in 33.4 volts. The capacitor is 35 volts, so we're still okay. But here it comes. The grid is not always exactly 230 volts. It actually has a 10% allowed tolerance. Taking that into account results in 36.7 volts, which is way more than you would expect at first glance. Even if you subtract the diode voltages, the capacitor will still fail fairly quickly. Electronics holds many of these landmines which you have to learn through decades of experience. I have a gift for you if you're interested. It's a free 1-hour design course and a checklist which explains many of these landmines. The link is in the description. Now you may say that 253 volts must be a pretty rare case. Well, our whole street has solar panels and on a nice sunny day the voltage regularly exceeds 250 volts. So let me show you the actual board I encountered these problems with. It's a protection circuit you see in the picture and it had two things going wrong. At this high voltage, the protection circuit never worked because I used the absolute supply voltage to make a threshold and it was too high. So I had to change resistor values. The first issue also meant that the load stayed at almost zero, resulting in the highest possible output voltage, which was breaking my 35 volt capacitor. So I had to change it to a 50 volt version. So I just showed you how high the maximum voltage can go. However, the voltage can also drop a lot in the other extreme, causing different problems. Let me show you. When the grid voltage is 207 volts and the load is maximal, you get just 22.9 volts. So the supply voltage range is 22.9 to 36.7 volts. That is a huge range. If you want a reliable design, you have to take this into account. This is why I tell my students to check capacitor voltage. If the voltage is too high, they'll fail. It's also important to check dropout voltages for regulators. A regulator fails if its input voltage is not high enough above its output voltage, causing a wrong output voltage, ripple and noise. So what do you do to prevent problems like this? First of all, check transformer datasheets and for small transformers, buy one and actually measure it. Second, simulate and measure your designs with the full grid range plus 5% extra margin so you are sure your design is bulletproof. For measurements, you can use a variable transformer to generate these extreme grid voltages. So now you know how to bulletproof your linear supplies. But here's the thing, if you make mistakes in your layout, none of that matters. So watch this next where I'll show you how to get the most of your layouts. See you next time.